the older name is, okay. These are basically code 360 today. The older name is basically MDM database. So let's think about an insurance company that wants to build a big database of all customers that it may have, right? So this could be in the millions of customers. So initially, it will send in a table of 10 million tuples. Every single tuple, this kind of person. So you need to do entity matching inside this table, and you cluster all the tuples that refer to the same person. Then you combine each cluster into a single canonical tuple. So now you have 3 million tuples, one tuple per customer. And that make up the initial MDM database. And then every week, you may actually have 300,000 new tuples of customer coming in. And you need to match those into the 3 million tuple already in the MDM database. And then you need to merge those tuples, right? So that is how you maintain the MDM database over time, by doing this entity matching all the time. There could be an insurance agent who is sitting somewhere and there's a new customer. And she may actually enter some information just to find out whether the customer is already in the database. So you need to also do real-time matching from this tuple into the database, right? So entity matching is clearly a fundamental operation to build up this MDM database, which is a very popular form of knowledge graph in industry. So the current state of the art is actually not that great. There has been a vast amount of work in the past 5 decades. Most of them focus on developing algorithmic solutions. Unfortunately, recent solutions are very complex. They usually addressing corner cases because that is how they got published, okay? They need to do something technically complicated. Very few entity matching work actually have built end-to-end entity matching system. Most of them are academic prototypes. They are not very good for real-world uses. There have been a lot of EM systems developed in industry, but most of them use handcrafted rule, and they're very good in certain domain, but very hard to generalize. Some recent systems have used machine learning, but they don't know how to scale so that they could match table of millions or tens of millions of tuples. Okay? So this is why we started the Magellan project at UW-Madison a few years back. What we wanted to do is to develop a platform that support entity matching end-to-end. We focus specifically on building systems. We want to apply those to real-world problems, uncover research challenges, solve them, incorporate the solution back, and improve the system. We really want to develop something that we think is basically the PostgreSQL for entity matching. So anyone wanting to do entity matching, they would actually start with Magellan, right? So we started initially in 2013, formally launched the project in 2015. We have developed 2 major systems by 2019. One is a PyMatcher, which is an open source on-prem EM platform in Python, and CloudMatcher, which is a closed source cloud-based EM platform. And these 2 have been used in many different real-world applications. So let me very briefly talk about PyMatcher. So PyMatcher was in development since 2015. It actually was a lot of work and effort, and has an extensive code base. And today, it is basically the most advanced and comprehensive open source EM system for our users, as far as we can tell. PyMatcher actually have been used in many different real-world domains. It actually have been pushed into production in many cases, as you can see in this column over here as well. It has also been used at many companies like American Family Insurance and several other companies. And I'm not going to go through the details of this. There's actually a paper that describes this in detail, and I put the paper at the end of this talk. So the other system that we have built is CloudMatcher. And the initial motivation for that is that we want to help domain scientists to use CloudMatcher to do EM. So if a domain scientist want to do entity matching, they should just go to the CloudMatcher homepage, upload 2 tables to be matched, and then they could just label a few hundred tuple pairs. The system should learn from that how to do matching. or they could even outsource the labeling to a crowd of workers, like on mechanical Turk, right? So that was the initial motivation. And here is a very brief example on how it works. So if you go to the CloudMatcher homepage, you log in. Let's assume that you have two tables that you want to match, table A and table B, and they describe restaurants, right? What you can do is you upload table A, you upload table B, and all you are doing is basically labeling a bunch of tuple pairs. So if you look at the first two rows here, these two restaurants seem to be the same. So you click yes. The next two restaurants also seem to be the same. So you say yes. The next one is clearly different. So you say no. And basically that's it. You just click yes and no and unsure for about anywhere from 300 to 600 tuple pairs. And you are done. The system will learn to match from that, and it will return essentially matching tuple pair for you, and you can download. So this is a very, very simple system to use. As I said, straightforward, easy to use. There's no required EM knowledge. The user basically just label tuple pairs, and it actually can scale to table of million or tens of millions of tuples. So at this point,
and hi, your audio is going in and out.
I'm sorry about that. I don't know why that's the case. Can you hear me now?
Yes.
Okay. I will try to stay still and let's see whether that works. Let me know if you have a problem.
Okay.
Yeah. So CloudMatcher has been used in 12 problems at 6 companies and organizations and in 1 domain science team. And there's a paper describing that in detail. It also got quite a bit of commercial interest and funding. And so I ended up doing a startup. I actually did not want to do a startup, but this is one of those cases where I could not refuse. So Informatica actually have invested in this startup, and we are now developing solution to push CloudMatcher into their enterprise entity matching platform. So for the rest of the talk, I will talk about CloudMatcher. I will highlight the most important idea behind CloudMatcher. This is basically state-of-the-art cloud-based, machine learning-based entity matching solution, as far as I can tell. Okay, so let's take a step back. So typically, when people do entity matching, they do blocking followed by matching. So typically, you cannot really compare all tuple pairs across the two tables because there would be too many of them. If you have 100,000 here and 100,000 here, you would have 10 billion tuple pairs. That would be too many, right? So the first thing you do is you use some heuristic rule to very quickly reduce the number of tuple pair you need to consider. You may say, I will only look at tuple pair where the two states agree, because if they don't agree, then they cannot match, okay? So in that case, you would never look at the tuple A2 and the tuple B1 because the two states are not the same. So if you do that, then you will quickly have a much smaller number of tuple pairs to look at. Now you could have a matcher, which is either rule-based or machine learning-based, and you could apply to make prediction, yes, no, that kind of thing, right? So basically blocking and matching are two fundamental steps, and pretty much any entity matching work will go through these two steps, okay? So in CloudMatcher, a key distinction is that blocking and matching use very expressive rules, much more expressive than current state of the art. And this rule will be learned, okay? So let's take an example. So for blocking will use a variety of similarity measures like exact match, Jaccard score, dice, cosine, and things like that. For example, Jaccard, you know, if you're gonna compute that based on two names, then the first thing you're gonna do is you do alphanumeric tokenizing. So each name becomes a set of tokens. And then you're gonna compute intersection over union, and that gives you the Jaccard score, right? The overlap score count the number of overlapping tokens. So in that case, in this case, it will be 2, and so on and so forth, okay? Now, let's see how blocking happens in CloudMatcher. So if you look at this table right here, it has ID, title, release, artist name, duration, thing like that. So this is basically a table of sums, right? Blocking in CloudMatcher will use a set of rules on this. So example of rule could be something like Jakarta, alphanumeric title less than this. So this rule basically say that if two titles are not very similar, Jakarta-wise, then drop the tuple pair. Don't even consider that. The next rule basically say if artist name are not very similar, cosine-wise, then again drop the tuple pair. And then you have a bunch of other similar rules like that down here, right? In practice, this rule could look pretty complicated, right? So now for the matching step, we are basically using a very well-known machine learning method called random forest. So a random forest is basically just a set of decision trees, like these 3 trees that I show over here. And when you have a tuple pair, you convert into a feature vector, then you apply all 3 trees, and you take the majority voting. Okay, so if 2 trees say no, then you say no for the entire random forest, right? So if you really think about that, a random forest is basically a set of matching rules. Suppose you have this random forest over here with 2 trees, right? Then basically the first decision tree encoding 2 matching rules as you go from the root to a match node. So you have 2 rules like that, and that will be these 2 down here, right? The second tree encoding 1 matching rule, so that's what you have. So again, a random forest is basically, you know, a bunch of matching rules. So basically that is the kind of rule that we use for blocking and matching. So now let's talk about how we're gonna do blocking, or rather how we're gonna learn it, okay? So here's a very simple baseline solution. We're gonna assume the 2 tables A and B have the same schema. We're gonna examine the schema and we're gonna create features just to be useful, like a Jakarta, you know, edit this, then exact match. We're gonna write blocking rule using these features, like this rule down here, okay? Then we're gonna apply the blocking rule to A and B. The simplest solution is to enumerate all tuple pairs in A and B. We're gonna convert each pair into a feature vector. So if we have a pair like a A1, B1, we're gonna convert into a vector of 4 numbers because we have 4 features up here, right? And the same for A1, B2, and so on. Then we're gonna apply the blocking rule to the feature vector. Now, of course, this is impractical because the number of pairs could be very high, right? So you basically have 3 problems here. How do you create the features? How do you learn the blocking rule? And how do you apply the blocking rule efficiently to 2 tables, right? So next, I'm gonna talk about these 3 things, okay? So we're gonna create feature automatically. Every single feature like this is actually having 2 attributes in the table, a tokenizer and a similarity measures. So the typical form is gonna look like this, right? So obviously we could write a bunch of rules and we could use the rule to automatically create the features. So this one right over here is showing an example of that. So given a particular attribute in a table, we're gonna first profile the attribute to understand, is it a single word string or multiple word short string or multiple word long or numeric or categorical or set value. And based on the attribute type, we know what kind of similarity measure we should apply. And there's some intuition on why, right? So we're gonna basically use this similarity measure together with a bunch of different tokenizers, and we can generate all kinds of features, right? So we could generate 20, 30, 70 features. So that is what we do in terms of generating features. Now, how are we gonna learn the blocking rules? So the general algorithm is we're gonna take a sample S of tuple pair from A and B without enumerating the Cartesian products, of course. Then we're gonna convert each tuple pair in S into a feature vector. So we're gonna get a set S prime of feature vectors. We're gonna learn a random forest F on that using active learning. Then we're gonna extract candidate blocking rule from F. Then we're gonna find and return a good rule sequence, okay? So this is actually a fairly complex algorithm. For example, take the sample S. We cannot randomly sample a bunch of tuples from A and a bunch of tuples from B and pair them together and get a sample S. Because if we do that, then the sample S would contain very few likely matches between A and B. So we need a sample in a much smarter way. And we have a couple of papers describing that. We're not going to talk about that because of time reason. I'm just going to talk about how do I learn a random forest and then extracting the rule from that. Okay. So to learn a random forest on a sample, what we do is that we start with two positive tuple pair and two negative tuple pair that the user is going to supply. How do we find this is yet another interesting problem that I'm not going to talk about. But given this, we can now actually train a random forest on 4 label example here, right? Then we're going to check on whether we should stop. A very simple thing to do is we just run the active learning for 30 iterations. So we don't stop here. We're going to next select, 20 most informative unlabeled example from the sample S. Okay, this could be example where the random forest is unsure. So maybe half of the tree in the forest say yes, half of the tree in the forest say no. So because of that, obviously, the forest cannot be sure. And so those are informative examples. So we take those 20 examples, we ask the user to label those, we add them to the original 4, then we retrain the random forest. Then we select the next 20 examples and we keep doing this loop. And we're going to do this for, say, 30 times or until when a stopping condition is met. And then we have the final random forest. Okay. So let me give a quick example. So let's say that I have 2 tables A and B, and A has 3 tuples and B has 2. So let's say that I take a random sample, not random, a sample of 3 tuple pair, right? I convert them into feature vector, right? Now I actually do the active learning on this, right? So let's zoom in on the active learning a little bit. So again, I have the feature vector, okay, from the sample. So let's say in iteration 1, I actually start with only 1 positive example and 1 negative example. So this would be my seed. So I convert them into feature vector. I have the label. So clearly I can train a random forest. I have the random forest. I'm going to apply it to each tuple pair in the original sample. So let's say I apply here. I have plus, minus, plus. Based on this, I select BD as the most controversial example. So I let the user label this one as just say a positive. So next, I'm gonna add that together with the 2 seed. Now I have 3 label examples. Convert them into feature vector, train a new random forest, apply them to the remaining example in the sample, select the next controversial example, ask the user to label that, and so on, right? So I just basically do this for 30 iterations. And the reason we do active learning is because this is a very good way to require minimal effort from the user and yet obtain the most informative example to label, right? If I am given 5,000 label example, of course I could train a random forest, but that would be 5,000. This one is more like a 500 example, okay? So active learning is very good in terms of minimizing the user effort. Okay, so now suppose I have finished with active learning and I have obtained a random forest. So the one you see here is a random forest of 2 trees to actually match books, right? So now I could go into the tree and I could pull out the rules going from the root to any node with a no leaf node. And I could think about that as a passable blocking rule. So this very first part right here basically say that if ISBN number do not match, then discard the tuple pair. This second one say ISBN number, if they match, but the number of pages do not match, then again discard the tuple pair. So those 2 become passable blocking rule. that I put down here. From the second tree, I could pull out 3 rules, right? So now I have a total of 5 rules. Not all of them are accurate. So what I could do is I could make the user evaluate the precision of those, right? And I would basically keep only the precise rule. So let's say that now I have only 2 rules that are precise as a blocking rule, right? I could apply all of this rule, but it's better to actually apply only a subset of that. So in the next step, given a set of blocking rule, we want to find a subset of rule that we can apply, and in a particular order, because a different order will run in different time, okay? So intuitively, the goal is to find a rule sequence that when applied, it will minimize runtime, will produce a candidate set that is as small as possible, and will retain as many true matching pairs as possible. So there's a solution for this using results from data stream. I will not go into detail. Again, the detail would be in a paper. So now let me talk briefly about applying the blocking rule, okay? So let's imagine that we have actually found a blocking rule sequence, like a R1 and R2 over here. So how would we apply it? So the key idea is that we're gonna assume that rule contain well-known sim functions, like edit distance, Jaccard, cosine. We're gonna exploit property of this function. We're gonna build indexes, then we're gonna use them to avoid enumerating the entire Cartesian products. So as an example, suppose I have a blocking rule like this, okay? So this is just one predicate, right? So if I have a string, like the big sort, then the number of tokens here is 3. Based on a well-known research results, we know that any string, if they pair with this string and they survive this blocking rule, then the length must be between 3 and 4, okay? So that means that if I have this string over here, the length is only 2, I know right away that there's no way that it would survive this blocking rule together with the big short. If I have the second string like this, the length is 3, then it's possible. So I could pair it with a big short and then evaluate this rule on top of that, right? So this gives us an idea on how to use an index on length in order to speed up this process. So again, if you look at this blocking rule, let's say that you have this table A, right? You could build a length index for A. So for length 3, we know from the index that only string number 3 and string number 5 has the length 3, right? So now if you go through, sequentially go through table B, and you pick the first tuple, which is the big short, we know that the length here is 3. We also know that the length of any possible suitable string in table A need to be between 3 and 4. So we could immediately go into the index, and we can see that we only need to pay attention to string 3, 5, and 6. So we go up here, 3, 5, 6. So we pull out the strings, and then we pair with the big short, and we just run it through the Jaccard word blocking condition, right? So basically, that's what I showed out here, okay? So at the high level, what we do is we take the rule sequence, we convert that into a positive CNF rule, look like this. For every single predicate in the rule, we try to infer indexes, and then we build them. And we do this using Hadoop. Recently, we use Spark. And then for every single tuple T in the table B, we're gonna probe the index. As I mentioned earlier, we find a small number of tuple in A that could be suitable. And then we basically pair with the tuple in B, and then we apply the rule to that, right? So all this is done using either Hadoop, or recently we actually use Spark and MongoDB, okay? Okay, so now blocking is done. Okay, so once we finish the blocking, we have a bunch of tuple pair. So now we're gonna get to matching. And matching is a very much like active learning for blocking. So if we apply blocking, we have the tuple pair, set of tuple pair C. We will now define a set of features based on schema A and B. The setter feature typically richer than the setter feature for blocking because blocking is expensive. So we're gonna use fairly cheap features. We convert C into a setter feature vector C prime. We do active learning on C prime to get a random forest G, which is a matcher, right? Then we're gonna apply that matcher to all remaining pair in C prime to make prediction. So that is what I showed down here. You can see that there's an active learning, you get G, and then you apply G, okay? So that basically gives us two possible workflow templates. If table A and B are small, then I'm not gonna do blocking. I'm gonna take the Cartesian products, convert the tuple pair into feature vector, and then I basically just learn a matcher using active learning and then apply the matcher. Otherwise, I need to do blocking. So I take a sample, convert tuple pair into feature vector, do active learning to get a random forest, pull out the blocking rule, evaluate them, select an optimal rule sequence, apply them using Hadoop or Spark, then get the candidate set C, and then do the matching part, right? So basically, this is the high-level process. So that wrap up my talk. Let me conclude. So what we are doing in the past 5-6 years is that we have been developing Magellan, which is basically, we view that as like a PostgreSQL for entity matching. We have developed two major systems. PyMatcher is an open source. They could be used. They are a little bit neglected right now because we are pretty busy with our startup and Informatica. CloudMatcher is unfortunately closed source. We wanted to open source that, but then we got acquired, so we are not allowed to open source anymore. CloudMatcher uses very expressive and powerful blocking and matching rule. They learn this rule from label data via active learning, and we need to combine not just machine learning, but also big data technology and effective user interaction to make this work. This we view to be a major step forward for entity matching research and development because we have a very new innovative system platform. We demonstrate how machine learning can be used effectively. There's actually a research highlight article coming up in communication of the ACM that I can send to you. And this also suggests very similar system-centric solution for other data cleaning and integration tasks that we are trying to develop. So there's also a bunch of paper about overall Magellan project. There's a paper about CloudMatcher. We also have done a lot of work on using deep learning for entity matching, and I'm very happy to send more details. So that's it. Thank you.
Thank you, Anai, for an excellent presentation. The questions can be pasted in the QA chat. We will move on to our next speaker, Yuxiao. Yuxiao, over to you.
Okay, thanks. Okay, can you see my screen and hear me?
Yes.
Yeah, okay. So hi, everyone. This is Yuxiao from Maxwell Research. Thanks for having me today. So today I'm going to introduce our recent work on inferring the academic, inferring knowledge graph in the academic domain. Okay. So let me direct jump into the focus of today. So we are actually currently working on the Maxwell academic graph, short for MEG, and currently the academic knowledge graph contains more than 230 million publications that are published over the past 2 centuries, starting from the year of 1800. Okay, so on the y-axis, it's the number of publications per year. Okay, so and it is in log scale. If you look at the linear line in log scale, meaning that we basically found that the number of academic publications over the past 200 years doubled every 12 years consistently. Okay, so those 200 million of publications include the journals, papers, conference proceeding papers, scientific books, technology patents, and preprints, and so on. And they are authored by hundreds of millions of scholars from a lot of academic institutions. They were published in journals, conference, and they study about hundreds of thousands of research topics or fields. So in Mag, we call it field study. Okay, and the benefit or the advantage of the academic knowledge graph can power the power many of the business applications. For example, one is the Microsoft academic search system. So basically, the academic search system in Microsoft is a semantic search system. So by semantic meaning that the academic knowledge graph I just introduced to you that powers the search experience. So next, I will take probably 2 or 3 minutes to show you how the academic knowledge graph powers the semantic search experience. Okay. Okay, you should be able to see the Microsoft academic search system. So by semantic search experience, I mean, you can actually input any entity that you are interested in. Say you are interested in any topics, authors, institutions, or journals, or conference, or any combination of them. Say you are interested in Stanford University, right? It will recognize Stanford University as an institution. And if you get the search page, result page, it will show you on the right top corner the system based on the academic knowledge graph. It recognizes Stanford University as a research institution. And in the middle, it shows all the publications by Stanford scholars. On the left, it shows the different types of entities associated with the institution Stanford. Okay, like the top topics associated with Stanford, like computer science, medicine, things like that, and the top authors in Stanford in terms of scientific impact, and the top journals, top conference that Stanford scholars are publishing at, and also the public institutions that Stanford scholars are collaborating with. Okay, so the power of the knowledge graph that powers the system is that you can actually input anything here. Say you are interested in how Stanford University scholars are the research about, say, COVID-19. So you can actually, right, search. The system will try to recognize, say, okay, Stanford University, this query means the institution, and COVID-19 you input, you are actually mean coronavirus disease 2019. Okay, it will show you all in the middle all the papers published by Stanford on COVID-19, and on the left again it shows you some basic entities related to both Stanford and coronavirus COVID-19. Okay, similarly, say if you want to say how Stanford is doing in artificial intelligence, you will try to recognize Stanford's efforts in academic efforts in AI. So say what are the top author entities in Stanford who are doing research about AI? You can see Chris Manning, Andrew Ng, Fei Li, and say Richard Stalker and Ulrich Koch and so on. Okay, and also you can, if you are interested, say Ulrich Koch, you want all his all his paper published on one particular venue, say KDD. You care about his KDD paper published when he joined Stanford, say, I don't know, 2011, something like this, something like after 2011. The system will try to understand your query based on the academic knowledge graph behind. So it will get you all the 22 KDD papers Ulrich Koch published after 2011. Okay, so this is a simple demo how the academic knowledge graph powers the semantic search experience. And let me get back to the slide. Okay, so here is an example for academic knowledge graph. So in addition, we also host the Office graph that connects the different types of entities that are related to the Office applications like Word, Outlook, Excel, PowerPoint, things like that. And in the Office graph, you can see it has different types of entity like users and documents, table sheets, and calendar events, things like that, right? And essentially, linking economic graph is also be able to consider as a knowledge graph, and not to mention the Sartori knowledge graph that is powering Bing's semantic search experience. Okay, given all those graphs that we can consider as knowledge graphs, meaning that they are heterogeneous. They, in the sense, they have different types of entities and different types of relation, right? I think they have been mentioned in the course in previous presentations. So, in addition, most of them are associated with text information or document information. Say, in academic knowledge graph, it has publications. For each publication, you have the abstract title and the full text of this publication, right? And for office knowledge graph, you can have the Word document and the email text information. And often, even say most of the time in real world, those graphs are associated with time information, meaning they evolve over time. Okay, say, for example, the academic graph I show you, it actually contains publication over the past 200 years, right? Okay, given all those knowledge graph, we have actually lots of applications, business applications, and for most of them, to address them, they need to address associated machine learning tasks. And the common practice is that for each of those tasks, we try to train one machine learning model to address this task that is dedicated to this task. Okay, and here are those tasks specifically in academic domain. So here are some examples. The first one, very commonly, is entity recognition. Say, how do we recognize the student Stanford as an institution, UW College as a scholar, and say when you input Nature, we try to understand it's you mean Nature, the journal Nature, right? And this entity recognition problem can be even more challenging when it faces the name disambiguation issue. For example, in the Microsoft academic knowledge graph, it actually indexes tens of thousands of scholars published under the name student Jing Zhang. So the question is, how can we distinguish between, I mean, whether two Jing Zhang are the same person or not? Okay. Here is another interesting example from myself that a couple of years ago, I collaborated two people, both named Yang Yang. So in this case, it's even more challenging how to do the entity resolution, recognize these two people are different Yang Yang. Okay, and another example is for each publication, research publication, what are the research topics of this publication, right? And I believe one of the most common or most useful application for knowledge graph is recommendation. Say entity recommendation in academic domain. Say you are interested in the Journal of Nature. What are the most similar journal to Nature, right? We can see through the knowledge graph, it tells you Science, PNAS, and Nature Communications plus biology are the most similar to Nature journal. Okay, and similarly, if you are interested in what are the most similar academic institutions to Harvard University, you can see Stanford, Columbia, U Chicago, and so on are the most similar to Harvard. And similarly to Google, you can see Microsoft, Facebook, MIT, those institutions are most similar to Google in terms of academic publication. Okay. And another attempt, very recent attempt, we are trying to do is to reason about something from the academic knowledge graph. Say here is the example is because the academic knowledge graph index all the publications over the history about say diabetes. So whether we can reasoning something about diabetes, such as what are the symptoms of diabetes and what is the cause of diabetes and what are the existing treatment or potential treatment for diabetes, right? Okay, here is an example how we are currently doing. So we can actually, given all those medical entities, we can say on the left, we recognize those should be the cause of diabetes, and in the middle, the blue entities, they are the symptom of diabetes. On the right, it's the existing treatment and as well as the potential treatment for diabetes. Okay, very recently, we applied the same method on the COVID-19 publications. So we can see that it successfully inferred that SARS-CoV-2 and coronavirus are the cause of the disease COVID-19. Right? But certainly we can see the red one, they are the failure case. So it mispredict that MERS, Zika, and the Ebola virus are also COVID-19 the cause, which are not correct, right? And similarly to symptom, it show you the symptom that inferred from the academic knowledge graph, like asymptomatic, but the wrong case is on the rash one. And for the treatment one, those are currently being tested or potentially can be the cure for COVID-19 that we discover from academic publications. Okay, so those are all the tasks that we are interested in or we have to address in the academic knowledge graph. Okay, so as mentioned before, traditionally, given all those tasks, we need for each of them, we try to train or design a machine learning model to address them, right? The idea here we want to, or the question here we want to answer is that can we actually pre-train with the heterogeneous knowledge graph, right? And if we have pre-trained the model on knowledge graph, then we can somehow apply this model to address all those different inference tasks and its associated applications, right? This is the question we want to answer, whether it's possible or not. Okay, I guess everyone is familiar that the idea of pre-training models was original from the natural language processing community. So in natural language processing, the research has found that it's very effective to pre-train a language model. And when you have some new NLP task, you can leverage this pre-trained model and fine-tune it over this model by using the new task, the objective, or even the new data associated with the new task. Okay, the core of the pre-training procedure includes two parts, right? The first one is at the model level, we need one model that is able to understand or capture the internal relations inside the human language or natural language, right? At the task level, we need a task that as simple as possible that is able to guide the model to fully understand or at least try to fully understand the natural language, right? Often those tasks are self-supervised tasks, right? Like in BERT, it use the mask language modeling and the next prediction as the pre-training task. Okay, then if we want to apply the idea of pre-training on heterogeneous knowledge graph, whether it's possible or not, what are the potential challenges we need to address? So correspondingly at the model level, the currently machine learning or deep learning models, we say that they are not capable or strong enough to model the dynamic and the heterogeneous nature of knowledge graph. Okay, and similarly on task level, existing attempts or existing tasks on knowledge graph inference, like link prediction or knowledge graph completion, those tasks are not informative enough to guide the learning model to fully understand the knowledge graph that are associated with lots of different relationships. Okay. Also, finally, I guess the ideal case is that we need some tasks that don't involve manual data labeling, right? Because for labeling graph data, it's even much more challenging by labeling vision or language task. Okay. So to address these two issues or challenges at these different levels, so at the model level, we actually introduced the heterogeneous graph transformer. It is a model that with the promise that to learn the multi-relation dependency between different types of entities. And at the same time, it has the dynamics of knowledge graph in mind. And the basic idea is that for each type of relation, the model tries to assign and maintain a unique set of parameters take for example, the heterogeneous subgraph on this slide. Say we are interested in the target node paper T, and we have, say it has 2 source nodes. One is its author node S2. The other one is its citation paper S1. Okay. Given this heterogeneous knowledge graph with 2 types of relation, how can we model this graph? Okay. So I will briefly introduce the architecture or the flow of the model. So given the 3-node knowledge graph on the left, as an example, as the first step, it tries to calculate the mutual attention between the 2 source nodes and the target node, meaning the attention between S2 and T, as well as S1 and T. Okay. As the second step, it will try to compute the message that will be propagated from the source node to the target node, meaning again from S2 or S1 to the target node T. Okay, and the final step is to aggregate the attention in the first step and the message on the second step, based on specifically to each type of relation. Okay, so this is the basic flow of this neural networks or transformer model. And so this model basically, this design of this model basically models or captures the heterogeneous nature or multi-relation nature of knowledge graphs, right? The other challenge or the other issue is the dynamic part of real-world knowledge graph, right? So traditionally, no matter it's a homogeneous graph or heterogeneous knowledge graph, usually when we handle the dynamic part of the graphs, we actually, based on the timestamp, we try to split the graph into multiple graphs based on the timestamps, meaning that in each timestamp we have the graph stamped short. Okay, this procedure, or this this method, the issue with that is that by doing this, you actually lose the dependency between or across different timestamps, right? If one entity, it is for each entity, it's not only related to entity that within the same timestamp, it also relates to entity in previous timestamp and even in the future timestamp. Okay, right? So to address this, we propose, say, how about we maintain all the relations happening across different timestamps and allow the entities and the relations with different timestamps to actually interact with each other. Okay, to do this, the idea is very simple. We actually use the method we call relative temporal encoding. So if you are familiar with the positional encoding in BERT, it's very easy to understand on this part. So basically, it's a relative encoding for the dependencies across timestamps. Okay, on this part, I show you at the model level how we can design graph neural networks that is able to, or at least trying to fully understand the knowledge graph, right? But how about at the task level? What would be a simple enough task to guide the model to learn the multi-relationships in knowledge graph, right? So as we discussed before, the traditional link prediction knowledge graph completion tasks are not strong or informative enough to guide the model or the model we proposed or we presented before. Okay, so to address it, we actually learn from the contrastive learning. We present the event-driven NCE training, meaning the noise contrastive estimation training. So basically, this is a learning objective that a very simple learning objective that can guide a simple model to learn all types of relations at the same time. Okay, here is the basic idea how the event-driven NCE training works. Say, so for example, in academic domain, the event is the publication of each paper, right? So they author 1 and author 2 decided to collaborate and published one paper. So it was published in 2012, for example, and it was published in KDD conference, and it was about data mining. Okay, this is a real event happened in the academic knowledge graph. Okay, for each of these events, we try to construct fake event. Okay, say we construct a fake paper with some part of the relationships about this paper is correct. Say we still keep its author 2, keeps its venue KDD, but we actually randomly switch its author 1 with another author 3, and we randomly assign its topics into security. Okay, the learning objective for the model is then basically try to distinguish between the true event, the true paper, and the fake paper. Okay, based on its relationships across, surrounding this entity, this paper entity, or this event. Okay, this is the basic idea of the pre-training task to guide the heterogeneous graph transformer model to understand the multi-relation structures in the knowledge graph. Okay, so although the idea is very simple, but theoretically we can actually easily prove that optimizing this objective is equivalent to maximizing the lower bounds of the mutual information between the heterogeneous knowledge graph structures and each event you are interested in. Here in academic domain, it's the publication of each paper. Okay. So in summary, so we introduce the pre-training strategy of pre-training strategy with a knowledge graph, particularly with academic knowledge graph. So at the model level, I show you how heterogeneous graph transformer can be effective or expressive to learn the different types of relations or dependencies in the knowledge graph with time in mind. And at task level, we show a very simple task without any labeled data to guide the graph transform model to learn or to understand the knowledge graph itself. Okay, and let's get back to all the tasks we are interested, like the name distribution, like the paper topic, inference, things like that, over the hundreds of million scale academic knowledge graph. Okay, so we are not going to dive into the detail of the results. So basically, the heterogeneous graph transformer model at the model level itself offers around 10 to 20% improvement over the existing graph neural networks, and the pre-training strategy offers another 1 to 5% improvement over the graph transformer model. Okay, so this is the result for the model part and the pre-training part. Okay, the interesting part I want to show you is one case study. So this is what the pre-training model tells us about the entities in the dynamic academic knowledge graph. Say, for example, if you are interested in the web conference, WWW conference, so it turns out that the model said that in 2000, the model is, the conference is very similar or very interested in database networking and information retrieval topics, meaning that you can see it's very similar to, in 2000, the year 2000, it's very similar to Sigmod, VLDB, NSDI, GlobalCom, right, and Figure. But 20 years later, this year, it turns out the web conference is very similar or more interested in the data mining problems like KDD, and as well as the existing topics like networking, database, and information retrieval, right? Okay, and for KDD conference, say, in 20 years ago, it was a very traditional conference. I mean, close to traditional database and data mining conference. But nowadays, it turns out KDD is very open to machine learning, database, the web, artificial intelligence, and natural language processing, right? So, and for NeurIPS, before it was about computer vision, machine learning, and AI. Nowadays, it's also about deep learning and natural language processing. So this is what the model tries. The model explains to us about the entities, how the entity evolves over time in the academic knowledge graph. Okay, so in summary, again, so we show how the heterogeneous graph transformer and its pre-training strategies can help us understand the different relationships in knowledge graph, particularly in academic knowledge graph. And also, I want to show that the Microsoft academic graph with hundreds, 200 millions of publications, and all those entities and the relationships and the time information and abstract information, things like that, completely open and free to download and to use for academic purpose. You can actually download the sign up to download the full data at this link. So you can also search it on search engine to get the link of the data. So feel free to use it for your any purpose. Okay, that's all I want to introduce today. Thanks again.
Thank you, Yuxiao, for an excellent overview of Microsoft Academic Graph. A lot of interesting problem and challenging problems, and your solutions are very interesting and fascinating.
Okay, thanks.
Move on to our next speaker, Georg. Georg, over to you.
Yeah, thank you. Let me try to. Can you see the screen? Hello? It's not happening. No.
No, not yet.
Not yet. Let me again try to share the screen. Can you hear me?
Yes.
We can hear you, but no screen yet.
No screen yet. And yet? No?
Not yet.
Not yet. So I don't know what's happening now. Here. I click on screen sharing. Let's see what that is. So again, let me try to share my screen. Does it work? No.
Not yet.
I don't know what happened. It worked so well before. That's really bad. Just can't. I click on screen sharing and nothing happens here.
If you want, you can email one of us the slides quickly, and we can present for you.
I have the slides.
Yeah.
It'll be better if Georg can control it.
Yeah, that would be.
Oh,
really
wait, it just came up. It's
yes.
up now. It's
Yes.
up now, Georg.
Very good.
Yep.
Okay, so what's that here? Hopefully. Does it work now? Yeah.
Yes.
Very good. So this talk is about Badalog. It's a kind of logical language, a Datalog style language. I will also explain what Datalog is, but it's also a system. We have a Badalog system, and we are taking it commercial. We already have 6 or 7 customers. Go down here. So this is a larger view of our system, and it also, this is the so-called Badalog flower, as we call it. So we have a big space for reasoning, and we have a repository for rules. So the rules are stored with the system, but as you see, no data are stored with the system directly. So our philosophy is to use the data storage of the company where this is deployed, or of an institution where this is deployed. So we don't have any, we don't require users to use any particular format. Of course, internally we will use a format, and that's Datalog, but Datalog is such a versatile language that you can basically communicate with every other, with databases, with machine learning, with analytics packages, OLAP, Internet of Things, etc., etc. So no, it's not that we have done all this. We have a very good database interface right now. We have interfaced with machine learning, and we have interfaced with web data extraction, but I can't speak about that today. We have also interfaced with systems like DLV, that's a disjunctive logic programming and answer set program, which allows us to also solve NP-hard problems in case it is necessary. What is reasoning here? What do I understand by reasoning? Reasoning is we have data and we have rules and a so-called ontology, and I would prefer to say rules, and we have already heard today about several types of rules. Yeah, and these rules generate new data. So these red points here are new data that are generated by the rules. Now, these red points can be either generated on the fly when you need them, or they can be materialized and stored somewhere in a database. Now, many people think that when we speak about knowledge graph, a graph database suffices. That's a common error that the industry makes. Of course, not the people, not our speakers today, but of the other speakers, but many people say, oh, I want to have a knowledge graph. So I buy a graph database. That's, of course, not what we want to do. You cannot really reason, or you cannot, there's no reasoning built in the graph database. So what I want to stress here is that reasoning tasks are required that cannot be expressed by description logics, for instance, and cannot be reasonably managed by relational database management systems, nor graph databases. And I will speak about such reasoning tasks. But now here's a very, very simple one. You have Wikidata contains the statement, Taylor was married to Burton starting in, so I have a window here. Do you see this window here? No. You see the slide, and I see another window here. Anyway. Taylor was married to Burton starting from a year and ending in another year. Actually, she was married twice to Burton, and this can be represented in a relational database in data log notation by married Taylor Burton 6474. So that's a tuple in a database, and this is just the logical notation for this tuple. And then now we have a database where we have this data, and somebody asked, when was Burton married to Taylor? And the answer, there would be no answer. And so you have this rule is a data log rule that you can add to the database, and in a certain sense, you can make the database more intelligent with such a rule. And you say for each u, v, x, y, if u and v is married during the interval x, y, then also v and u is married. So basically, it just expresses the symmetry of marriages, of the marriage relation. And even such a simple rule can unfortunately not be expressed with standard description logics. And as you see here, there are universal quantifiers. Very often we will just omit them when there is no probability of misinterpretation. Now here I will give you another example. We have a lot of companies here. So this is really a large graph. This is actually an existing graph where our system is used for. It's a very, very large graph of companies. And you see here an ownership relation. Of course, I give you here a simplified description of what we have done here. So this means, for instance, this company owns 25% of this company, okay, etc. And now you want to define a rule, you want to define what it means a company controls another company, okay? So what does that mean? And you can define it through a recursive rule. It's very hard to learn such a thing. It's very hard to learn that by machine learning. So you can say, first of all, you can say in natural language, a company X controls a company Y if X either directly holds 50% of Y or X controls a set of companies that jointly hold over 50% of Y, okay? Now, so here I have simplified this a little bit. I've simply said a company controls itself. And then these two rules are both actually in this rule here. If X controls Y, if X controls Y, and if Y owns fraction W of a company Z, and if we sum now over all these Y's, yes, and over all this W for all these Y's, so that's a kind of group by and aggregate function here. And if the sum of this, yeah, is greater than 0.5, then X controls Z, okay? So this is a typical recursive rule. This is not just a data log rule, it's a little bit in an extended language where we also have aggregate functions and arithmetic here. And we have a kind of aggregate functions that work on monotonically growing databases here in this case. It's monotonic monotonic aggregate functions. So of course, such rules cannot be expressed in description logics and very clumsily in database languages like SQL. Okay, you can do it in SQL, but very, very clumsily. And it's very complicated to understand. And I think this rule is much easier to understand because it basically corresponds to what is written here. Well, I have here changed the first line, but you could also say directly encode the first line here. Okay, so this is a rule that in a certain sense expresses knowledge. It expresses knowledge because it's very hard for a machine learning program to discover such rules. There are approaches, but it's very difficult, and also you would not know if that's then precise. So this is a rule that is part of law and regulation, and it comes from humans. And of course, you want to be able to process such rules too. Now, I give you now another example, a funnier example in a certain sense, but an example that really happened to me, and that also shows you that we really need rules, and we really need common sense rules and rules, or expert rules also, rules that come from humans, however. So this is an example about my own credit worthiness. I live in 3 countries, actually, not only in Austria and in the UK and in Austria. Also, my wife is from Italy, so I spend a lot of time in Italy. And I have several credit cards. So this is an Italian one. These are our UK credit cards. This is actually an American one, but in the UK, and that's an Austrian one. And that's a credit card that I hide the name, the real name, so I call it Sandbank. So I wanted this Sandbank credit card because it has very, very low fees and a very good exchange rate. So it would have been very nice for me to have this credit card. And actually, I asked for it, I applied for it, and I got it. But as you see, the credit limit on this card, unlike on other cards, is only 500. What can you do with a credit card with a credit limit of 500? Not very little, not very much, maybe, sorry, especially if you travel with your family, etc. So what happened? So I was very angry, and I phoned this bank, and the bank said, well, that was not us, that was the credit rating agency. So I phoned the credit rating agency, and I asked them, and they said, well, it's very difficult for us to determine why this is so, but let's look into it. Let's call back in 3 weeks. So I called back in 3 weeks, and they said, we still don't really understand what the algorithm did, but we have the most modern machine learning program, so probably this is right that you should deserve this credit limit. But I can only tell you one thing, it's related with the house where you live, okay? And then I understood, at this moment, I understood everything, because I had moved into a new house, and before I moved there, I visited the house, and I saw a gentleman there, very nice gentleman actually, who was the tenant of the previous owner. But after I moved in, I got a lot of letters for him. And unfortunately, sometimes I opened some because I thought it was for me, and it were all unpaid bills, and people were knocking at the doors and say, where is this gentleman? He owes me money, etc. So what basically did the machine learning program reasonably learn? It's actually, from a statistical standpoint, pretty reasonable. People who live in a joint household with somebody who does not pay their bills are likely to fail repaying their own debts. Yeah, so that's a reasonable rule. It's ethically, of course, highly questionable. And this rule, however, was applied to incomplete and wrong data. Why was it applied to wrong data? Because obviously the machine learning program thought that this gentleman is still living in the house and I'm also living there. And then it applied this rule to me. Now, clearly, basically, if somebody buys a house and moves in, it's common sense knowledge that the tenant of the previous owner has moved out. Only in very, very few cases, maybe my auntie was a tenant of the previous owner. Yeah? Then maybe she had stayed in, but that's maybe in 0.5% of the cases. But in 99.5% of the cases, the previous tenant had moved out. So this is a typical expert knowledge that we want systems to be able to deal with too. Okay, so what we believe is that machine learning should be complemented and where necessary actually overruled by domain-specific expert rules that express domain knowledge. A new domain knowledge could look like this, and of course you can put that then in logical rules. A new house owner is most likely unrelated to a previous tenant. If a house is bought by somebody who did not live there previously and now lives there, then the previous occupiers have most likely moved out. So you see, these rules are probabilistic rules, and of course we will be able also to process probabilistic rules. If somebody has closed their bank account without opening a new one, that was also the case for this guy, then it's likely that the person has moved out of the country. In fact, the previous tenant has moved to Iceland, and much later, 2 years later, I read a newspaper article about him involved in a big scandal in Iceland. So as you see, applying such rules would be interesting. This is typical expert knowledge, and so a human expert rating agent or a human expert rater would apply these rules and would say, oh, this guy is in. Certainly the other guy is still in the database because we didn't get any signal from outside that we should eliminate this guy from the database. Yeah. So they are both in the database, but the database is of course a very lazy database that is not updated because we don't get signals, the right signals to update this database. And so clearly we should give a good credit rating to this guy, to me. Okay. Now, what is for me, therefore, a knowledge graph management system, or what should it be actually? It's a knowledge-based management systems plus big data. It must be able to handle big data, and it also must do analytics and machine learning. And in a certain sense, in order to, let me just misuse the so-called lateralization or brain lateralization thesis just for illustration. We all know it's not very clear, but there is something to it. Yeah, if you speak to neuroscientists, the right part of the brain is works more like machine learning and neural networks and recognizing, and that's why it's so good in pattern recognition. And even in game playing, because game playing is recognizing when is a configuration of a game a winning position. And the left part of the brain is more language-based, rule knowledge, logical reasoning, etc. And in an unknown way, nobody has understood how they work together. So here, the example would be that you have rules here, but these rules take the effects from the other side of the brain where they are recognized by some symbolic neural mechanism. So we really need both actually for intelligence, and we expect that in the future knowledge graphs will be able to to have both components and not only machine learning or not only logical reasoning. So let's come back to our system. So as I already said, our system is built around reasoning, but we also have machine learning and a very, very loose way of coupling this reasoning to machine learning for the moment. In the future, we are, of course, many people, not only we, are aiming for a much tighter coupling between machine learning and reasoning. So now we have some knowledge that is vertical knowledge for certain verticals. For instance, we have a knowledge base for oil and gas, for life sciences, banking and finance, credit rating could be another one, etc. Then we have so these are verticals, these are application-oriented knowledge bases. And then we have general knowledge layers that are used for many people, like entity resolution, for instance. Entity resolution, we have heard the first talk today by Angel Down. Entity resolution is, as we have seen, important in many, many sectors. It's a kind of transversal feature. And so we have built it into our system. We are also using web data extraction because we are interested to get data from web pages directly into our reasoning system. We use data wrangling because every time you do reasoning and machine learning tasks, you need to get your data, you need to transform your data before you really start to do it. And graph analytics, but this is now not social graphs, but this is graphs like these companies, for instance, where we find nice ways to process these graphs. Okay, and below this we have the core reasoning engine. Now I want to speak now about the language that we use. This language is called Vadalog. It's core Vadalog. It's a very simple language, and then we add arithmetic and a lot of other features to it. So what is core Vadalog? It's full data log. So we already have seen a data log clause that was this marriage clause, plus a restricted rule of existential quantification. In rule heads, stratified negation. So a type of negation where we can say, if this is not true, and this other thing is true, then conclude that. And so why do we have existential quantifiers in rule heads, in addition to data log? Well, we have them for several reasons, and I will just show a few of them. Data for data exchange and data integration for data extraction, for reasoning with RDF, and for ontological querying. Doing what description logics usually do, we can do that also, but we need existential quantifiers for it. And then there are other applications for existential quantifiers that I don't mention here, that I don't illustrate here. Product configuration, for instance, and conceptual modeling. You can model UML with it. Okay, let's go to data exchange. Very simple. Data exchange means you have one database, you have another database. So one database, the source schema, the other database has a target schema. Let's imagine these are just relations, single relations here, but you can do it with entire databases. And you have here an employee, last name, first name, address relation. These are the attributes of the relation. And here you have another relation, and you want to learn from both, but you have to first, let's say, merge these relations. But here there's an attribute birth date, and instead of last name, instead of address, you have birth date, and here you don't have the birth date. So how can you fill the data in? Well, you create basically you could use this rule, employee XYZ implies there exists a W. You know this person must have a birth date, but you don't know its value. Person X, Y, X, W, okay? So this W here is a kind of existentially quantified variable, but when we process these rules, then this variable will be replaced by a null value, by a so-called labeled null. As null value is a specific label, and we know this is a specific birthday, but we don't know what exactly it is. And then we can still answer queries. For instance, we could answer even for a person coming from here, from this relation. Does this person have a birth date, sorry, and therefore a birthday? And the answer will be yes, even if we don't know this birth date any longer. Yeah, because we know there is something, and that this something stands for a concrete value, but it's just that we don't know it. Now let me come to data extraction. Web data extraction. So web data extraction means extracting structured data from unstructured web content. And we have worked a lot on this very much. If there's time, I will come back to it at the end of the talk. So you see such a table on the web. Yeah, and you think, well, that's a nicely structured object. Here you have the products and here you have the prices. But actually it's not. It meets your eye, but it's not, because it's programmed very often, and that happens more often than you may think. It's programmed in form of two tables that are just put next to each other, okay? But there's no logical relation between these two tables here, okay? Just for the user, for you, if you look at this table, you see one table because they have the same color, and they're just next to each other. So people program a lot with diffs and with other elements for HTML programming, and actually the logical structure of the information is very often not in the web page. And if you do data extraction, you have to rediscover it. So you have to use a kind of deconstructivist approach here, and try and deconstruct what is this? This is a table, this is a table, and then you construct another object out of it. So first you deconstruct, and then you construct. And constructing a new object needs object creation. And so you could have a data log rule that says table T1 and table T2. And if T1 and T2 have the same color, okay, and if they are immediate neighbors, is neighboring right, T1 and T2, of course you have to define this predicate with some other clauses, then there will be, we create, in the process of analyzing this web page, we create a new object, that's T, and we call it table box, and this object contains T1 and T2. Okay, and then you could write more things. You could write T1 is a table, T2, you can write a lot of, this is just an example. But as you see, very often if we analyze things, we have to create new concepts, new objects, and these new objects here, in this case it's even a concept, a new concept. This new object that instantiates this concept table box is indicated here through an existential quantifier. Now, reasoning with RDF, let's go back to our marriage problem. Taylor married Burton during this interval, and you want to have it to do a symmetry rule. Now, if you are RDF, you only have triples, and triples could be predicate, subject, object. Okay, so here the predicate is written first in logical notation, but that is exactly an RDF triple. So you could, for instance, say spouse K1 Taylor. This tuple could be this 4 tuple here, quadruple or 4 tuple here, could be 5 tuple actually, because you have a predicate here also, but forget about that in this moment. Spouse 1 K1 Taylor, spouse 2 K1 Burton. So K1, as you see, is the key for this. Now you have to tie these four RDF triples together with some key. Spouse K1 Taylor, spouse 2 K1. So the second spouse in the marriage is Burton. And that's the start of the interval, and that's the end of the marriage interval. Okay, so you could depict this in form of a graph here, which could be part of a knowledge graph. And then how would this rule, our rule, translate for each UVX? Y married UVXY implies married VUXY. How does this rule translate? Well, this is the symmetry rule for marriage intervals, and it now becomes a little bit more complicated, but we find that we can do it, because what we have to do is we have to construct a new construction with a new key. And the new key can now be constructed with an existential variable. Spouse UY1, spouse 1, sorry, UY1, spouse 2, UY2, start UY3, and UY4 implies there exists a new key that encodes in a certain sense a new relationship about more than 2 objects, such that spouse VY1 sorry, that should now be Y2, and this should be Y1. No, sorry, it's correct, because that should be spouse 2, and that is spouse 1. Start with Y3 and end with Y4. Okay, so here in this case, because RDF is very limited to triples, we had to use an existential quantifier, and that's why we can do a lot of things that also we can do actually everything that RDF can do with our language. Now let me come to the final application of existential quantifiers, and that's description logics and ontological reasoning. And here I just show you a very, very nice description logic family called DL Light family. Why is it so nice? Because it has a very low complexity, and with big data, complexity is a very important thing. And in these description logics, you have very strange formulas. Professor included in exist teaches too. And now we can just write that in our language, which we now call data log plus minus. Why do we call it data log plus minus? Because we extend data log, for instance, by existential quantifier. We also extend it by this button sign, which means false. And minus because we have to restrict it, and I will speak about these restrictions later. Okay, we have to restrict the bodies so for good complexity and decidability. So this rule here translates to for each x, if x is a professor, then there exists some y such that x teaches to y. Not always true, but let's assume it's true. And professor included in not student just means for each professor is not a student. This is also not true in practice, but assume that there's such a rule at the university. Okay, if x is a professor and if x is a student, then there's an error. And has tutor minus included in teaches to can now also be translated into a rule for each xy, has tutor xy teaches to yx. And then we also have some functionality axioms. Has tutor is functional. So for each x, y, z, if x has a tutor y and x has a tutor z, then y must be equal to z. Okay. So as you see, these description logics also very nicely fit into our formalism of Waterlog, which is one language of a bigger family called data log plus minus. And however, in certain cases, we need the existential quantifier. So with pure data log doesn't do the job. Now, if we just added the existential quantifier to data log, so if we took full data log augmented with the existential quantifier, unfortunately, this would immediately become undecidable. And there are several proofs of this in different contexts. This has been shown. So what we have to do is finding expressive, and I would also say efficient, decidable fragments of this very simple language, data log plus existential quantifiers. Okay, so that's why, as I already said, data log plus minus, we put some additional goodies to data log, like stratified negation, the bottom sign that we can use to say that something must be false, cannot hold, existential quantifiers, and others. Yeah, for instance, some restricted arithmetic functions. And Waterlog and minus means we must restrict this, and I will show you about the restriction, which kind of restrictions we have. So Waterlog is a member of the data log plus minus family, which admits very efficient reasoning methods, which can be easily used and with a good complexity for reasoning. Now you may, those who have seen last week the talk by Marie-Laure Meunier, she has also studied such languages, and she has, for instance, found this very beautiful and large language, which is called weakly frontier guarded. We have previously defined a language called guarded. Here is data log. You see that guarded does not comprise data log. Weakly frontier guarded does it. This is the description logic DL Light. This is another description logic, and this is another logic called sticky logic, which I don't have time to talk about today. What I want to show with this slide here is that there's a lot of research going on to identify some really nice decidable fragments of extensions of data log that capture a lot of things. So, and what Waterlog, the core of our Waterlog language is approximately situated here, is this big red oval, and it captures data log. It contains data log as a sub-language. It contains DL Light, the description logic as a sub-language. It captures another language, so-called linear data log plus minus as a sub-language. But it is not as, it is a subset of weakly guarded, but weakly guarded, unfortunately, is very complex. To reason with regard to this double exponential time complete, and to reason in data complexity, that means even if you keep your theory fixed and you're just looking at the complexity when the data is growing, then you are still exponential time complete. And that's what we unfortunately cannot afford with big data, and that's why we are looking at such languages. So here's another picture that's more the complexity picture. So if we just add just the existential quantifier to data log, you are undecidable, you can simulate Turing machines, you are Turing complete if you want. Then you have this other big, very expressive language, very nice language, but unfortunately very complex to execute. Then we have core Badalog. Core Badalog is p-time complete, like Datalog, but it has also existential quantifier and some other goodies. And then we have also identified some smaller fragments that are higher, that can be better parallelized and that are even more efficient and that can be executed on parallel computers. So now I will explain you what restrictions. So Badalog is of course a restriction of this. So I will try to explain what kind of restriction it is. This looks a little bit more complicated, but the nice thing is that almost every time you need an existential quantifier. We haven't found one application where this restriction doesn't hold. So in general it holds, and it can be checked. This restriction that I will show you now, which is somewhat technical, can be checked automatically. Okay, so you have here a set of rules with existential quantifiers, and I first want to define what the affected positions are. So what are the affected positions in these atoms here, yeah, for these predicates? Yeah, affected position is a position where basically an existential term, also called a Skolem term, can flow in. So here you see, obviously, the W comes here in, so this third position will be affected. This first position will also be affected, and this second position will be affected. So these positions are affected, but they are not only affected here in the head, they are everywhere they are affected. Where this T occurs, this third position is affected. Yeah, that's clear. The third position of a predicate T is affected. And what you are doing now is, you are simply continuing with a kind of symbolic evaluation of this and to say, okay, this C is here and it's transposed here, so also this must be affected, etc. And with the other rules the same. So at the end, if you get a fixed point of this procedure, and you have determined what are the affected positions, and very simple, these are positions where existential and existentially quantified variables could flow in values of null values, so-called null values, because I've already explained that these existential variables will be replaced by null values. They can flow in. Okay, and in some positions they can never flow in. Okay, of course, whether they flow in or not, that depends on the data that you give to this program. These are just rules, and if you execute these rules over data, it could be or it could not be that some existential comes here. But in the worst case, they can come here. Now we define what dangerous variables are. What are dangerous variables? Dangerous variables are variables that occur in the body of the rule, that also occur in the head, so a head variable like this X, and that only occur in affected positions. So this X in the body only occurs in an affected position. Yeah? There's no other place in the body where it occurs, and as you see, it's underlined, so it's affected. This Y also occurs in the head, but it doesn't occur, it is affected in this body, but it does not only occur in the affected position, it also occurs here. And since this variable must of course have the same value whenever this rule is executed here and here, and given that it is not affected here, it can never bind to any null value, it can never bind to any existentially created value. Okay, and so therefore, even though it is affected here, it's not dangerous, because actually it will not contain null values, and it's not, even though it occurs somewhere in an affected position and in the head. And in a similar way here, the C is affected. The Y doesn't occur in the head here, so it's not affected in this rule, this variable. And the X is affected here, just like it was affected there. There's no Z here, and this Y doesn't occur in the head, it's not affected. So these are, these are our dangerous, these rectangles show us the dangerous variables. So these are dangerous.
So here we have about 5 minutes.
So now, thank you. Now, what is Badalog? Basically, the basic core of Badalog are rules where all dangerous variables must, in each rule, must jointly occur in a single atom, which we call the ward. Okay, so here this affected variable occurs in a single atom, this occurs in a single atom, this is a single atom. Okay, so this is called the co-Waterlock. So that's the definition. With this definition, we can guarantee that this program will remain polynomial. First of all, is decidable, will remain polynomial. But the nice thing is that we can express so many things. So what we are looking is languages where you can express a lot of things, yeah, and which are still very efficient. And for instance, let's look at the symmetry rule for marriage intervals. Is this in co-Waterlock or not? So is this in co-Waterlock or not? Here we have an exists V. Now this exists V does not at all occur in the body. Okay, so no variables can be dangerous here, because the existential variables, yeah, they don't occur. The new existential variables here don't occur in the body, so it cannot be affected. It cannot be, sorry, dangerous. Yeah, the dangerous variable is a variable that occurs in the head and in the body and only in affected positions. But this occurs only in the head, so there's no problem. Yeah, dear light. Here, of course, this variable occurs only in one atom. Yeah, this variable why it doesn't occur in the body, so this rule is okay. The other rules are just kind of data log rules, so they don't create problems. So this is also part of Waterlock. So now Waterlock is, of course, can be extended with a lot of other features like data types, monotonic aggregations, as we have already seen, probabilistic reasoning, various types of probabilistic reasoning. We can also have some equality atoms in it. And we also have primitives that bind relations directly to relations in databases. So we can make a database query, and then the relation R in our database, in our Waterlock program, will be filled with all tuples from the external, thousands of tuples, and we have a paging mechanism that we don't have to bring them even all together into the main memory. How do we interact with machine learning? We have several interaction models. Currently, we use only one, but we have several others in mind. So basically, the interaction with machine learning is really, really very simple. And it's not, of course, what we ultimately want is our two brain parts that are closely working together. But still, for a beginning, I think it's quite good. We can prepare data. Our programs, Waterlock programs, can send them to machine learning. We get the results, for instance, annotated classified data from machine learning back into our core reasoning engine and can continue to reason with this. Now, the second type would be that we basically define some predicates, classifier predicates, and whenever we call this predicate, the machine learning process is asked the classification. So that's a kind of almost a syntactic variant of this. The interesting variant would, of course, be more interesting, and we are also working on that, but being a new project, is to have machine learning learns rules, and these rules are retranslated into Waterlock rules, and then these rules work together with the Waterlock rules. So that's our ultimate goal, but that's research right now. The other things here, this year is already implemented and works in industry. Now, we have good algorithms and good curves for machine learning, for Waterlock processing, compared to even MySQL or other databases, Postgres, Oracle. We have tested it. Crucial question is this: can we do useful things with this combination now? With machine learning on one hand, it's an external thing, but we have a very good API to it, and reasoning over big data. Yes, we have many applications. Fraud detection in bank, that's a commercial project we have. Credit worthiness, as I have already explained. Logistics, we are now investing a lot in logistics, supply chain criticality. Security in companies, fully automated web data extraction. We have actually, our project has started from another project where we wanted to not just create wrappers by hand, but fully extract web data from a specific domain like real estate or used cars, etc., and fully automatic from thousands of web pages, extract the data and store the data in the database. And in order to do this, we really use also rule-based reasoning and machine learning. Machine learning, for instance, for page classification, for visual clue recognition, etc., and other things, page exploration strategy and navigation planning. Global decision making is made by rules. And I want to conclude my talk, but we can, of course, maybe I could already answer questions by showing you a video, a very short video that shows this hybrid system that uses machine learning and rules. So it goes to the first, it has a list of thousands of web pages, it goes to the first web page. It has already recognized where the input fields are, and now it tries it out, it tries the input fields, it immediately clicks there.
We are not seeing anything, so I wonder if...
Oh, I'm sorry, you cannot see this. I will, unfortunately, I can't show you the problem. Thank you for mentioning this to me.
I think that's okay, we're pretty much out of time.
I will send you a link to this system, okay, to this demo. And
yeah,
then
we can link it to the course website.
Yeah, I will link it to you. You can link it to the website. Yeah, thank you very much for your attention.
Yeah, thank you, Georg. We have a few minutes for a discussion. Anhai has left, but we have both Georg and Yuxiao, and let's have a little discussion. As Narendra is looking for audience questions, I have a question for Yuxiao. I'm curious to know, how is Microsoft Academic Graph different from Google Scholar and Semantic Scholar that AI2 people have built? What are the key distinguishing characteristics?
Okay, very good question. How about let me discuss it in terms of purely research perspective. So first of all, our definition focus is on the semantic part, meaning that we have knowledge graph supports the Microsoft Academic Search System. And as far as we can tell right now, Google Scholar is more focused on keyword search. So you can also search the Nature Journal, KG Conference, Stanford University, things like that, right? Or you can also search COVID-19, the research topics I think at this moment. And for Semantic Scholar, we actually have a very strong and deep collaboration. So Semantic Scholar, from its name, is also semantic focus. I think previously, I think a couple months ago, Semantic Scholar covers only or mostly on medicine and computer science publications. We actually cover 19 top level, like physics, chemistry, things like that, arts, psychology. This is one distinction. So the coverage, we are way much more larger than Semantic Scholar. The second one is, I think our collaboration right now with Semantic Scholar starts to powered by actually Microsoft Academic Graph. So yeah, okay. That's what I would say.
Okay. All right. There is a question for Georg, which is interesting question that, Georg, have you, instead of using Verilog, have you tried to use natural language?
Microphone? Okay. I just answered it, but anyway, yes, of course, we have thought very often about this. It's possible in principle. It's not very difficult. It's just whether we use natural language for such a very limited fragment of logic, that's pretty easy, yeah? But actually, and so why would we do that? Because many companies, we want to sell this product to companies, and we do. Some companies take it and are happy and work with this. Even some banks, they really like Verilog, but other companies says, no, that's a non-standard language, etc., yeah? So what we did is, instead of natural language, we just use SQL. So that's the next version of our system, will be completely Verilog free, and it will have SQL statements that you can plug in instead of each Verilog rule, which doesn't mean that the SQL, each rule is executed only once, but there's a big fixed point around, yeah, that computes the rule, the recursion over the rules for the entire graph. And this is much easier for some people like that much more, for whatever reason, yeah, because probably they learned at school, at the university, they learned SQL, and SQL seems familiar to them, yeah, even if there's a big loop around that then computes the kind of fixed point. But this is very easy to do, and then people suddenly say, oh wow, this is standard SQL. We can use it.
Okay.
But we could do it.
Well, I think that's fine. That's a fair answer. So the question for Yuxiao would be that, in the context of Microsoft Academic Graph, do you ever encounter situations where you feel the need for rule-based kind of reasoning that Georg talked about?
You're on mute.
Yuksha, you're on mute. Yeah.
Yeah. Okay. Yeah. So you mean rule based, right? Not I mean the comparison between rule based and the learning based. That's the question, right?
Yeah, I think Georg's architecture was that, well, you should have learning-based system, but you should also couple it with rules because you need rule-based reasoning also. And the question to you is that yours is heavily learning-based system. And do you encounter situations where you feel that, well, wouldn't it be nice if we could just write this in rules?
Yeah, we actually have many rule-based parts in the system. So I mean, at least so the rule-based techniques can be considered as the first attempt, also as the baseline for comparison with the learning-based system. Let me think about some example. Say like name disambiguation, right? Say these two authors. I think there is one audience asking about whether we use the ORCID ID or not, right? So we actually use that part of information. So you can consider that as part of the rule. Like, I mean, automatically from this data. So yeah.
Yeah. Can I may add something maybe?
Yeah.
So we have used also entity resolution, and we have noticed that for some specific things, it's very good to have. Sometimes you need complex rule types. For example, if you want to analyze URLs, yeah, that's standard knowledge. You don't want a machine learn what a URL means. There are several rules expert rules that can decompose a URL into domain, subdomain, etc., in order to know whether they come from the same person. So you have IBM dot Germany and IBM dot etc. There's a fixed meaning to it. We don't need, and here we used rules and we could improve actually machine-based entity resolution by using such domain knowledge, expert knowledge, basically about, for example, the composition of what is the meaning and the semantics of if you can speak about semantics, of URLs. Yeah.
Yeah, good point. I agree. So, yeah, I guess following your point, I guess we're actually also using rules on URLs, like you mentioned after this. Like say, if we found the academic publication, the index in Stanford.edu or MIT.edu, we'll assign based on rules a high value or high confidence that this publication is very good or nice. Yeah, cool. Thanks. Mm-hmm.
There are a few questions for George.
Yes.
One of them is, does that mean you are just using the SQL syntax with the Verilog semantics? But what are other?
Absolutely.
Yeah.
Absolutely. We are using SQL. I mean, we don't have that yet, but that's the next step that we do because we have seen that people don't like Verilog and love SQL. Yeah. And so we give them SQL, but we translate immediately the SQL into a Verilog rule and use our system inference algorithms for this. Yeah. And the thing is, the SQL statement is standard SQL because in one step, yeah, just execute the rule once. Yeah. That corresponds to one SQL statement, to a standard execution of SQL. And then we just say, well, we iterate that because we have to go over the entire knowledge graph with many, many nodes. Yeah, we iterate it until it stops. And that's the fixed point. And that people like that actually. It's much easier for them for strange reasons to understand than Verilog. Yeah. Okay.
There are a couple of more questions for you on the Q&A panel.
Yeah, so one question is, you criticize description logics by saying that you cannot specify married relationship. Why isn't it as simple as declaring that the relationship is symmetric, which you can very easily do in description logics?
Cannot, it's not so easy to do in description logic. I mean, first of all, the description logic doesn't have variables. Yeah. Well, you could say X is included with symmetric. You can say if you have a binary relation, yeah, you can say this is included in the other one minus. So you need two inclusion relationships. Yeah. So that you could say, but there are many things that you cannot say in description logic. So think about our banking rules, ownership rules, and also with 4 tuples you cannot do it. So you have to encode everything into binary relations. Yeah, for description logic.
So I have a question for Yuksha. I mean, Microsoft Research Academic Graph has a very rich and interesting set of relationships which evolve over a period of time. So in your system, do you have some kind of a data model or a semantic definition of what your knowledge graph is actually modeling?
You mean the relation types between entities, things like that, or?
Well, I mean, I think the people like us who are coming from data modeling background,
Okay.
they think of data models in terms of, say, entity relation diagram or some kind of a formal graph model that we can query, and from there we can see what are the specifications of different relationships in your graph.
I mean, like in the live demo I showed, so when you search each query or each entity, when it recognizes, it will constrain the data associated or relation associated with each entity that the system at least recognize. So that's I guess part of the answer. So meaning that we have a data modeling or data structure behind to index all those relations, semantics, efficiently given the size of the graph.
Yeah, so I mean, I've read the Microsoft graph papers, and I really found that if it can somehow be combined with a formal language which makes the graph semantics explicit, that could be very interesting, and it could provide a way of adding additional domain knowledge and domain expertise of the sort Georg was talking about. Yeah, so unfortunately we are out of time. We must end here. So I'd like to really thank our speakers for giving us an exciting overview of their research and how it affects products. We look forward to seeing you again next week at the same time. Thank you all very much.
Thank you.
Thanks.
Stay safe. Bye.
Bye.
I'm typing in here some answers.
Okay, I'll let you finish answering him.
So what do we have? Okay, that was answered. If you model it in description logics, then merit as a binary relation, that's possible. But we here have also a relation with intervals, with marriage intervals. It's a four-area relation. You cannot do with four-area relations in standard description logics, and then you have to encode it like I did with the RDF. Then it's possible, of course, yeah. But it's not so directly. You cannot operate on four tuples. The last question I found really interesting in the presentation. Is possible that Georg includes a link to his slides? Yeah, I sent the slides, and so they will be linked. Yeah.
Yeah. So link is on the web page.
Yeah. And to Waterlog real world implementations, given that there was no correct link to his bio or to his slides. Okay, I will try to put some links also for real world applications. I think they are on the web page of our company, or will be or are on the web page of our company, but also in the papers. I mentioned papers with real life applications. On the almost penultimate slide of my presentation, I have a reference list, and in this reference list, there is a data engineering paper in the data engineering conference, and there we mentioned a lot of real life applications of Waterlog. Okay.
Okay.
Forward rule. Then it says the last question. I was wondering if Waterlog supports forward rule processing in addition to the standard backtracking. Here I have to say Waterlog, we have both forward and backtracking algorithm, but in the current implementation, we have actually only forward rules. Yeah. So we are doing forward rule processing, and we are having a very aggressive strategy for blocking existentials, because existentials could lead to infinite databases. No? If I say every person is a father, if I do that forward, yeah, that's an infinite chain, even if it's probably not infinite in the world, but but we know that all queries of a certain length, if you fix the length, the maximum length of a query, then you don't need to propagate this chain infinitely, you can stop somewhere, and we do that in a pretty aggressive way, and that's why the system is also very efficient. And the mechanism that we use is called the chase. That's a specific mechanism for data log with existential quantifiers. But we also published in some of our papers that are on the list backward chaining algorithms, and in the future we also may want to implement them. I think that's it. That was the last question.
Yeah. So
Okay.
thank you again, Georg. I really appreciate your staying up late at night. It was a
No
pleasure.
problem. I'm a night owl anyway, so that's when I go to sleep, but usually I don't work at this time. I watch Netflix, one episode of something at this hour. Okay, thank you very much. All the best.
All right.
Bye-bye.
Thank you.
Bye.